did you get as the area of the green, or the parallelogram? 25 units squared. What did you get for the trapezoid? 30 units squared. The kite in the middle? 30 units squared. The triangle on the top? 21 units squared. And the rhombus at the bottom? Okay, what about the entire triangle? Or, sorry, rectangle. Okay, so for geometric probability, all you're doing is you're taking your desired space over your total space. Okay, so I wrote, because I don't have colors up here, but I wrote, like, this is red, green, yellow, blue, and green again, and then this whole thing in the back is white. Okay, so what would be the probability of landing on the red? You have 30 units on top, because that's your desired space. And then what goes on bottom? 234. Now you need to see in your calculator, does that simplify? 5 over 39. If I told you to convert to a percentage to the nearest tenth, what would that be about? 12.8%. Okay, if I look at the green space, we have two shapes that are green. We've got the parallelogram and the rhombus. So what is our total desired region? 41 units, because you have 25 plus 16 over your total region, which is 234. So like Ashlyn said, that's 41 out of 234, and does that simplify? No, but as a percent to the nearest tenth, it is what? 17.5. Very good. Okay, the probability of blue, what would be my fraction? 21 over 234. Simplifies 7 over 78, which is about 9%. Yellow? 30 over 234. Which we've already found, and what is that? 5 over 39. Which is 12.8%. Okay, how do you figure out the leftover white space? 234 minus all these shapes over what? 234. Very good. So what's the sum of all the shapes? What is it? 122? 234 minus 122 is what? 112. Does that simplify? And that is about what in percent? 47.9%. Very good. So if I am throwing darts at this paper, where am I most likely to land? White space. In the white space. Okay, so what you are going to do is turn your page. You are making your own probability, like experimental probability table with this diagram. So what I want you to do is I want you to rip off a corner of your paper, probably the top corner, okay, and make it into a little ball. It doesn't have to be super big, just like that size. And make it into a little ball. Try to make it as round as you can. It'd be hard, but... Okay. Theoretically, is what we just found, and we know that red is going to be 12.8%, green is going to be 17.5%, blue is 9%, yellow is 12.8%, and white is 47.9%. So theoretical probability is the one that you calculate, okay? So that's like without any human error, the theoretical probability that things are going to land in those are these percentages. However, we know that as we do experiments, there's human error, okay? And so it's not always going to look like these numbers. So we're going to see that and see if we can get close to these numbers with our own little experiment. So off to the side of your first table, I would make a little chart like red, green, blue, yellow, white. Okay, you are going to drop your little ball that you made, okay, onto your diagram from your elbow resting on the table, and then you just drop it. Okay, so not up here, not like right here, just from your elbow. And you're going to see where it lands. Okay, you might need to put some borders up, otherwise it's going to probably go off your paper. So you might need to put pencil, calculator, or something. But see where it lands. Okay, if it goes out of bounds, redo it. But get 20 good throws. If it's not working well for you, decrease the height at which you're dropping it. And then when you're finished, take your fractions and put them over 20 and figure out your experimental probability. I'll give you another minute. Okay, looking at your data and your percentages, are they close to the theoretical, super far away? What did you guys find? So some of you found that you're close, some of you found that you're pretty far away, okay? So this is how theoretical and experimental probability work, okay? I'm going to use this little spinner up here to kind of use an example, okay? So let's say I make some of my sections bigger to represent our sections. Okay, so this could be the red is going to be the white space, and we're supposed to be at 48%, 47.9%. Yellow is going to be at 12.8. Blue needs to be at 9. Oh no, I'm changing the other one. It's going to be hard to do. This needs to be at 9. $47.8. Okay, close enough. Okay, so this kind of represents our geometric probabilities, okay, our theoretical probabilities. So if we spin the spinner 10 times, and I'm just going to skip to the end. Notice how our experimental and theoretical aren't very aligned, okay? Now let's say that we do 20 spins. Okay, we're still pretty far off. We haven't landed on cyan yet. Okay, let's increase it to 50 spins. Okay, we're doing a little bit better, right? I'm going to jump to 1,000 spins. Okay, what do you notice as the number of spins increase? Your experimental and theoretical percent end up getting closer and closer and closer with the more chances that you have, okay, or the more events that you have. So for number 1, when it says compare and contrast the theoretical and experimental probability, what do you notice and why do you think this occurred? Which one changes? Experimental, okay? And you guys can just summarize as I talk. I'm not going to write all this stuff down. But your experimental probability changes, okay? Your theoretical probability should always stay the same because we all started with the same picture of 5 shapes, okay? So your theoretical should be the same across groups, but your experimental can change. What changes do you think could cause the experimental difference? Wind, height, the person in general, the force at which you're dropping it, the size of the paper ball that you made, how round it was. So all of those things are called human error, okay? And that human error, human little flaws, whatever you want to call them, okay, that impacts that experimental probability. Okay, that's why you have your theoretical and your experimental. So does that make sense? Which one does not change? Theoretical, okay, and then experimental is changing. Alright, turn the page. Problem number 2. A class is hosting a dart competition to raise money. The following 3 designs are under consideration. All of the dart boards are squares that measure 50 centimeters by 50 centimeters. For this situation, assume that a dart is thrown randomly at a dartboard and that the dart will land somewhere on the dartboard. Okay, which dartboard would give the player the greatest chance of hitting the shaded region and why? Okay, so let's look at the big bullseye. Okay, remember that we have a 50 by 50 board, making the radius of our circle what? 25. Okay, so what would the area of our circle be? Which is 625 pi. What is the area of our board?
2,500.
Okay, so how would we find the probability of this shaded region? Very good. And then what percentage is that about? 0.54? Okay, let's look at your 4 congruent circles. Okay, again we have a 50 by 50. Okay, let's find the area of one circle and then we need to do what? Multiply by 4. Okay, what is the radius of just one of these circles? 12.5. Squared is what? 156.25 pi. We need to multiply that by 4. So what do you end up getting? And what do you notice? It's the same. So you still have 625 pi over 2,500, and that was about 78.54%. Okay, let's look at the last one, tricky triangles. Okay, you know that both sides are 50, and you know that there's 6 congruent shaded triangles. So they gave you a hint. Okay, what is the base and the height of each triangle? 25. So what's the area of one triangle? 312.5. And what do you need to do now? Very good. Multiply by 6. And that is what? Okay, and our last step is finding the percent. So 1875 over 2,500. 75%. Okay, so which dartboard will give the player the greatest chance of hitting the shaded region? The first two, it doesn't matter, right? So either big bullseye or 4 circles, because they have the same theoretical probability. Questions on geometric probability. Okay, so your project this is what I was talking about, okay? You will get that next time, but your project is designing a ceiling tile with some sort of, not a floating sky with a bunch of shapes, okay? So you want to make a design incorporating I believe it's 8 shapes, and then you have to calculate the geometric probability, so the theoretical probabilities of us throwing darts at it and what would be the probability that it lands in those shapes. Okay, so you're making something creative, so if you want to start thinking already, that's fine. Something creative, and then you have to calculate the geometric probabilities of throwing a dart and it landing in each of your shapes. So it should be pretty easy. Okay, but again, do not just sit there until the skills check. Your skills check looks more like the problems on your homework, so make sure you're working today. Questions? Okie dokie.